Hello and welcome to week 4 of Advanced Algorithms. So this week our focus is going to be on network flows, which is a problem that you might have seen before in your DSA course. And what we are going to do is begin by sort of doing a bit of a refresher on the setting, recall what the problem is all about, and come up with some ways of attempting to solve it. And we will encounter also this lovely duality between maximum flows and minimum cuts. So that's the plan for this part of the lecture. And then we will talk a little bit about flow decomposition, which gives us a useful way to break up a flow on a network into certain component pieces in a manner that turns out to be quite useful, as we will see later. Now, once we are done with that, we are going to be shifting our focus to the concept of reductions in the context of flows. So you might have seen before how you can solve, for example, the problem of finding a maximum matching on a bipartite graph by simply reducing it to an instance of maximum flow, whatever that means. If you've seen it before, that's great. If not, then if you just stay tuned in, we are going to see examples of this sort in just a bit. So essentially what we will be doing is taking up a few examples of problems which may or may not have any resemblance to the network flow problem off the bat, but what we will be able to do is somehow transform them into instances of network flow which are equivalent, in the sense that if you manage to solve the network flow problem that you have constructed, then that's basically a solution also to the problem that you started with. And now this may sound a little bit abstract and may not even completely make sense, but I promise you that it will come together once we start looking at a few examples. So that's the plan for this week. We're going to spend the first couple of modules on just discussing the problem setup and algorithmic approaches to find flows and to decompose them. And after that, we are going to be looking at a few concrete applications. So I'm looking forward to this. Let's dive right in. So it turns out that the history of the network flow problem goes back all the way to the mid-1950s in a war setting, when a US Air Force researcher and a retired US Army general, Harris and Ross respectively, were trying to study the railroad network that connected the Soviet Union at the time to its satellite countries in Eastern Europe. And they wanted to basically figure out a way of cutting off the supplies that moved from the Soviet Union to these countries in Eastern Europe. And they wanted to do this by damaging their rail network, and presumably they were optimizing for causing the minimum amount of damage in terms of, well, also minimizing the costs involved in causing said damage. And the way they modeled it was as a graph. So they had 44 vertices representing the regions, and they had over 100 edges representing the connections between the regions via the rail network. And then they used essentially an approach that you would now recognize as a flow-based approach to figure out what's the smallest number of edges that they would have to remove to completely separate or isolate the Eastern European countries from the Soviet Union. So that's a bit of a historical anecdote. There are some very nice documentaries that talk about this at length, and I will have pointers to them in the notes. So if this sort of thing intrigues you, please go and look it up a little bit more. In fact, the classified report from the gentleman in the States, which studies this issue, is actually available, and it definitely makes for an interesting document to look up in this context. But let's come back and talk about formulating the flow problem in modern terms with our usual sort of notation. So the input to the flow problem is a directed graph, but also two special vertices that we will call S and T. And typically, a way of remembering why they're called that is because the S usually stands for the source vertex, and the T represents a target vertex. So we will call them S and T. We might sometimes call them the source and the target, respectively. And what we want to know, at least intuitively speaking, is the maximum rate at which some resource can be pushed from S to T across the network. And like we saw from the war zone application, you could also pose the question of what's the minimum amount of damage you need to cause in terms of, say, removing edges from this graph to actually completely disconnect S from T. And as it turns out, these are really two sides of the same coin. You're really asking, in some sense, the same question, even though they may seem like they're being formulated slightly differently. All right, so having said all this, let's now try and get to the concept of a flow, and let's try to define it in a way that helps us model everything that we have been talking about so far. So I could, of course, just write out the definition for you, but I think it's a nicer experience to build it out so that it doesn't feel magical. And let's just work through an example and ask ourselves what we need for the definition to satisfy so that it's an accurate representation of the kind of problems that we want to be talking about. So let's begin with a directed graph with two special vertices S and T. So here is an example of such a graph drawn out on the screen for you. And well, what we want to imagine really, as we said earlier, is that we want to push materials from S and have them reach T, somehow traveling across the network. So the first thing that we need to think about is, well, how do we demonstrate this movement? And by the way, it's sometimes helpful to have a concrete realization of these kinds of graphs at the back of your mind, because they make these examples sort of come to life. So for instance, you can think of this graph as representing, say, a road network, and let's say what you're trying to transport from S to T is a bunch of trucks that are parked at a warehouse that's situated at the source vertex, and all of these trucks need to move across these roads and somehow get to T. And the other kind of example that you can imagine that this graph is modeling is, let's say, a pipeline network where you want to model the flow of, let's say, water, for example. Or you could think of this as an intranet type of a network, and you're trying to think about, well, how do I get packets across? So whatever really feels reasonable, I think it's helpful to have such a application at the back of your mind. So let me just pretend that this is a road network and we're trying to move trucks across. And let's say that there are, about 10 trucks that are stationed at the source to begin with, and we want to get these trucks across the network. And I could say that, well, let's get 5 of these trucks to move along the SA edge, and let's get the other 5 moving along SB. Notice that I did this by writing down the number 5 across these edges, which might prompt the idea that perhaps a flow is basically a function that assigns numbers to edges. I think that's a reasonable starting point. So let's try and make a note of that. So a flow is really just a function that goes from edges to, let's say, real numbers for now, right? And well, I mean, let's just maybe look at our example again. So let me just put down some more numbers across edges. And now, if you look at this for a minute, you might immediately find it a little bit disorienting or suspicious because, for example, if you look at the edges that are incident on T here, if these numbers are supposed to represent the number of trucks that are showing up across these roads, then you can see that what we are claiming is that, well, there are 3 trucks going on the CT road and there are 20 trucks going on the DT road. So the number of trucks that have showed up at T is actually 23, as opposed to, remember that we had 10 trucks that started out at S. So somewhere along the way, we seem to have magically manifested additional trucks, which should strike you as a bit odd. Of course, you could say that, well, maybe S is not the only warehouse. Maybe there are a few others. There are a few other locations where there are just spare trucks on the standby and we just got them mobilized via this flow. But that, well, is a slightly more general setting than what we are interested in right now. So we're going to assume that there's only one place that can manifest material, and that is going to be the source. No other vertex can magically create things that move along the network that were not already sourced at S. Okay, so all this is to say that we cannot simply stop by saying that a flow is a function from E to R. It has to be a function with some additional properties if we want the function to truly reflect the kind of applications that we are looking at. So this function certainly not cutting it. If we just continue our story from, the trucks leaving the warehouse at S, well, let's think about what happens at this junction here. For instance, at A, we see that there are 5 trucks that are landing up at A. And since we just said that we don't manifest additional trucks at these junctions, we know that if you consider all the roads that are going out of A, it must really be these 5 trucks that distribute themselves along these roads. We could simply continue the description of our function by saying that, well, we have 3 trucks that choose the A to C route, and let's say 1 truck each that chooses the A to B and the A to D routes. So far we seem to be doing well in terms of not creating any magic material. What about S? Well, what I mean is, what about the SB edge? The SB edge also had 5 trucks going in. And, can we just assign the number 0, for example, to everything else? Well, again, this would be slightly problematic because it would somehow imply that these 5 trucks basically came into B and got stuck there. They never moved on. And just like we said that we are not going to manifest new material at any location, we also don't want to have material getting stuck at intermediate locations. So the idea that a vertex in this network can actually hold on to some of this flow and keep it there and let it sort of be stuck there, that's something that we don't want to allow. So the flow really must just keep going. So basically there are 2 aspects to the constraint that I'm talking about. One is that, well, there's nothing new that comes out of a vertex. The other aspect is that there's also nothing that gets stuck at a vertex. Okay, so if you have 5 trucks incoming into B, then we need all 5 of those to actually get out as well. So we're going to push 5 trucks coming in from the SB side, but actually notice that at the junction B, you also have 1 truck coming from the A side. So there are a total of 6 trucks that are coming into B. They don't have much of a choice for where to get out. So we're just going to have to push 6 trucks along the BD edge. Now let's come to, well, the CD, or rather the DC, the CT and the DT edges. What's going on here? Well, let's think first in terms of D. So D has 7 trucks that are incoming, and the 7 trucks may well just all choose to take the shortest path, so to speak, to the destination vertex, which is D. So they may all choose to take this route, and that would be fair. So nobody goes up to C, so we have a 0 flow there. And at C now we only have 3 incoming trucks, and now the only choice is to go further down via the CT edge. Notice that nobody can come down here because these edges, as you will notice, are directed, so we can't have trucks going in the wrong direction on a one-way street. So that's basically what's going on. So now this is much nicer. We see that the number of trucks that have landed at T is now 7 plus 3, 10, which means that everyone who started out from S made it safely at T. But really, if we only care about getting 10 trucks across from S to T, we didn't have to do such a sort of a fancy distribution of these numbers. It would have been enough, for example, to find some path from S to T and just direct all the flow along that path. So that would also be a perfectly valid way of doing it. So for instance, here we have S to A, so let's assign a flow of 10 here, and then we have A to C, another 10 there, and then from C to T, another 10 there, and it's 0 everywhere else that's not specified. So is this a valid flow based on the property that we just talked about, that nothing gets stuck and nothing gets manifested? Well, this seems reasonable because, well, we said that we want to push a flow of 10 starting from S. So that's all baits are off at S. You can manifest material at S. But now that we have 10 trucks on their way to A, we know that A has to push all of them out, and A indeed does that, but along just one edge, which is the A to C edge. At C, you'll notice that there's an incoming flow of 10 and an outgoing flow of 10 as well. So we're all good. This satisfies our constraints. And then you might say, well, you know, what's really so interesting about this? Because all this means is that we can sort of do even a BFS, for example, starting at S, and at some point the BFS navigation will catch T. So you have a S to T path, and you just push all the flow you want in the world along this path, and you've basically gotten materials across. So what are we even trying to analyze? Well, it turns out that it may not be always feasible to push flow in this fashion. So for instance, if we continue with the idea that this graph models a road network, you might be aware that roads have different capacities for how many vehicles they can carry simultaneously. So you have like the service roads, the one-way streets, which are typically single lane, then you have 2-lane roads, and then this goes all the way up to 6-lane highways, for instance. So one of the crucial constraints when we try to model real-world problems using the notion of flow is the fact that not every edge is the same. Not every edge can hold the same amount of material as every other edge. And this is even more stark when you think of this as being, for instance, a pipeline network where you're trying to get a certain amount of water across, let's say, from the source to the target. And here, for instance, if the pipes have varying diameters, then there's going to be different values of flow that they can actually handle. So it's a fairly natural idea that each of these edges comes with what's called a capacity, which you can think of as sort of another function that maps edges to reals. So you're just going to say there's a capacity function, and you might even think of this as a capacity constraint, because this is what tells you that you cannot push your luck too much. So for instance, if the edge from A to C has a capacity of 3, then that means that it's going to be illegal to try and drive 10 trucks across from A to C. Now you might say, well, maybe we do it in batches, right? But remember that we really just cannot hold material anywhere. So for us to do it in batches would mean having some of the trucks stop somewhere. And that's something that's, well, it's not feasible in our current model. Okay. Think about, for instance, the pipeline network. So assuming that we don't burst any pipes, you really cannot send more than what you might think of as a bottleneck flow. So let's say that, for instance, this edge has a capacity of 5 and this edge has a capacity of 7, then this whole path here from S to A to C, and C to T is really only as good as its tightest edge, and which you might think of as a bottleneck edge. So in this example, it's the edge AC, because even though SA and CT have higher capacities, if you only want to push flow along this path, then you cannot push more than 3 units of flow, because in some sense the edge AC with that capacity will block any flow that is more than 3. Okay, so and that's why it's an interesting problem. So now let's say I'm still really for some reason hell-bent on pushing 10 units of flow from S, then we know that we cannot push all of it along this path, so we start exploring alternate routes. So perhaps, you can still push 5 along SA, but since we know that AC can handle only 3, perhaps we push some of the remaining flow along the other 2 edges. And of course, how much we can push along those 2 edges will again depend on the capacities of those 2 edges, right? So it's very natural to want to conserve flow at every vertex, and it's also very natural to imagine that the edges can't hold an unlimited amount of flow, because then you can just find the shortest ST path and push as much flow you would like along those paths, and that's not really a particularly interesting situation. So I think now is a good time to summarize everything that we have just said and make it official by introducing some terminology and notation perhaps. So first, let's recall that we said that a flow on a graph G with these source and target vertices being denoted S and T is simply a function that assigns a number to every edge such that it satisfies the conservation constraint. So let's write down what the conservation constraint is. We want to say that for every vertex V that is basically not the source or the target, we have that all the flow that comes into V, so that we are going to denote by the flow function on edges of the form U to V. So this is all the incoming flow. At V. You want to say that that's the same as all the flow that is going out of V. And like I said, this is something that we want to be true at every vertex, and we make exceptions for the source and the target vertices only. Of course, this is not to say that the source and target do not conserve the flow. They may or may not conserve the flow, but it's usually of interest to situations where you actually have a non-trivial net flow coming out of a source. In fact, that brings us to the next natural notion, which is the question of what is the value of a flow. Value of a flow F is basically an idea that captures the actual amount of material that you were able to transfer from S to T. That's what we want to think of as its value. So again, a reasonably natural way of defining this value, which I'm going to denote as sort of the cardinality of F, if you like. So this is the value of the flow F. We're going to define this as the net flow that goes out of the source vertex. So let's look at all the flow that's going out of S. And we said that this is the net flow, so we have to subtract the flow that's coming into S. And notice that for most vertices, and indeed for all vertices other than S and T, this value would be 0. But the value of a flow is really what was the extra that you had at S at the end of the day. And notice that when we did our example, the extra that we had at S was simply 10 because we had 10 trucks moving out of S. We didn't have any coming back in. So that was 10. And by the time we completed the description of a correct flow function, we also had 10 trucks arriving at T. And I want to say that that's actually no coincidence because the amount of flow that goes out of S is also the amount of flow that comes into T. These two quantities are the same. And if you guessed that that's happening because of the fact that the flow is conserved at every intermediate vertex, you'd be absolutely right. You can apply the conservation property to derive that the amount of flow that we have is indeed the same in terms of the net flow coming out of S and the net flow that is landing at T. Okay, so let me just introduce a little bit of notation that will turn out to be useful. So we are going to use delta of f of v to denote the net flow out of v. That is to say, you look at everything that is going out of v. So this is a sum over fvu. But then you get rid of everything that is coming into V. So that is FWV. So this expression captures the net flow that goes out of a vertex V. And as we have been saying, that's going to be effectively 0 for every vertex other than S and T. For S and T, there are no guarantees. But let's see what we can say about the total flow based on the fact that flow is conserved at every vertex. So let's take a sum of the net flow at every vertex. And I would like to claim that this is actually the sum of the net flows at the two special vertices S and T. And why is that? Well, as we sum over all values v, we know that these values are mostly going to turn out to be 0. And since we did not impose the conservation constraints only on the vertices S and T, those are the only two terms that survive out here, right? So hopefully this equality here is clear. But on the other hand, notice that this term here actually adds up to 0. And well, why is that? Let's again quickly recall what was delta of f of v. It was the total flow that was going out of the vertex v. So we said, let's look at the edges that are going out of v and the edges that are coming into v. And it's the difference of those two things, right? So now when you think of, any edge in the graph, so pick your favorite edge, let's say it's between vertices A and B. Well, the edge A to B is going to show up positively once. That's when you're computing the net flow out of A, and it's going to show up negatively once. That's when you're computing the net flow at B. Right? So when you look at the edge from A to B from the perspective of the net flow at B, then that's a negative contribution. And when you look at it from the perspective of the net flow at A, then this edge makes a positive contribution. So that means that every edge really shows up twice in this expression because you compute the net flow at every vertex in this sum. So every edge is going to contribute positively and negatively exactly once over the span of this entire sum, which means that all of these terms pairwise cancel out, right? Every edge appears exactly once positively, exactly once negatively. In some sense, we know that all the flow that's coming in is going out. So that's the idea. And that's why we know that this sum is in fact 0. And that's also why we already have a justification for the intuitive comment that I made earlier, which is that the net flow that goes out of S is the net flow that arrives at T, which you can think of as the negation of the flow that goes out of T, right? So that's what we have here from this equality. Now, so far we have talked about the value of a flow, and we have defined a flow as a function that assigns numbers to edges in such a way that flow is conserved at every vertex other than the source and the target. But we said that by itself this notion is not so exciting, because you want to think about questions like what's the maximum flow that you can push from S to T, and at this point there's nothing stopping you from defining a flow function that just pushes a lot of stuff across every edge and satisfies the conservation constraints. And you can come up with a flow, and your friend can come up with a flow that has a larger value than yours by just upping the stakes everywhere, and this can go on forever. So to make this problem really sort of anchored in something well defined and interesting, we have the notion of a capacity function which assigns a non-negative real number to every edge. And you say that a flow F is feasible with respect to the capacity function C if it turns out that the flow at the edge from U to V is at most the capacity of the edge U to V. This is a very, very natural thing to demand. You're not pushing anything more than what that edge can handle, right? If this was like a pipeline network where you're trying to push a certain amount of water, the capacity constraint is basically saying we're not going to burst any pipes, we're going to stay well within our limits at all points in the network. So we're really going to be interested for the most part in feasible flows. And let me also just introduce a few other words that we're going to be using sort of all the time. So the first word would be the word saturates. So we're going to say that F saturates the edge UV if the flow in the edge UV is precisely equal to the capacity, which means that you've really pushed this flow to its limit on this particular edge. So that's when you say that F saturates this edge. The other extreme is when F doesn't use the edge at all. So we're going to say that F avoids the edge UV if the flow in that edge is 0. That means we didn't use this edge at all. There was no flow going through this edge as far as F is concerned. And now we're ready to sort of define the max flow problem, which is basically the question of finding a flow of the maximum value given a directed graph G with a capacity function. So given G with ST and so on, plus a capacity function, find a flow of maximum value. And of course, this is a fairly bare bones model of the flow concept. You can enhance this with bells and whistles as you please. So sometimes you may want to say that, for instance, edges don't just have capacities, they may also have demands. You may have a requirement which says, well, I do need to push at least a certain amount of flow along a certain edge or along a certain set of edges. So that can be modeled using demands. And you can probably think of other things that you may want to sort of add to the mix here. But this is a fairly standard setup, and it's a good place to start. And thinking about how you can extend it to fancier settings is sort of a nice thought experiment. It's a good exercise to go through to just even come up with more enriched models for what you think of as a flow problem. But for now, we're going to stick to this. Just to quickly recap, we have a network, every edge has a capacity, the edges are directed, there are two special vertices S and T, and what you want to do is assign a number to every edge, which we are going to call the flow, which has the property, the assignment of the numbers is the property that flow is conserved at every vertex, and it's feasible in that it respects the capacity constraints at every edge. Now, as we have hinted to before, flows are deeply related to the concept of cuts. So that's what I want to define next. So to do that, let's pull up our flow network example again. So here we are with the graph and the designated S and T vertices. And now, what is a cut? Well, often one talks about specifically a ST cut to emphasize the fact that the cut is separating the source from the target. But if the source and target are clear from the context, then you might just use the term cut to talk about what I'm going to talk about now. So ST cut is basically a partition of the vertex set into two parts. So by a partition, we mean that you kind of break things up into two pieces like this, and these two pieces don't overlap and they encompass all vertices. That's what it means to be a partition. So we want S and T subsets of the vertex set such that they don't overlap. So S intersection T is empty, but they also contain every vertex between them. So every vertex either belongs to S or T. So we also need that S union T is the entire vertex set. This is what it means for S and T to be a partition. For this partition to count as a ST cut, it must divide S and T into two separate parts. So notationally, the tradition is to say that the source S belongs to the part denoted by capital S, and the target T belongs to the part denoted by capital T. So here in this example, I'm going to have to label this side as S and this side as T, and this would count as a valid cut. Okay, but the edges that belong to the cut are really what interest us. So let's focus on the edges that have their endpoints in S and T, and in particular, I want the head of the edge to be in S and the tail to be in T. I wouldn't care so much about edges that are coming back the other way. So for example, if this network had an edge going like that, I wouldn't particularly look at it in the context of the ST cut. So I'm really interested in edges that are going from S to T, and all of these edges here are said to belong to this cut. Okay, now if you had a capacity function on top of the network, then the sum of the capacities of these edges that are going across would be called the capacity of the cut. So let's say the edge AC has a capacity of 5, AD has a capacity of 10, and BD, let's say, has a capacity of 5 again. Then the total capacity of this cut right here is going to be 20. And notice that all the flow that you push from S to T intuitively must cross this cut, because if you were to delete all the edges that belong to the cut, so that's what we've done here. So here's the network with the edges that belong to the cut removed, and now you can see that once you do this, then there is no ST path whatsoever. And this again is not difficult to appreciate intuitively, because what we did was we split the graph into two parts. One part contains the vertex S, the other part contains the vertex T, and we basically cut off all the edges that could take you from one part to the other, right? So imagine that you have two islands representing the two parts of your cut, and there are a bunch of bridges that are rooted, in these islands that take you from one to the other, and these are one-way bridges. So all the bridges that go from the island that has the source or the warehouse, uh, from there to the island that has the destination or the target, all of these bridges, if they go missing, then there is no way that you can go from the source to the target. In this example, coincidentally, you also cannot come back from the target to the source, but the removal of the edges in this cut does not force that you cannot reach the target from the source. So for instance, if we had a couple of additional edges, which I'm going to attempt drawing now. So for instance, if we had an edge from T to B, and we also had an edge from, say, B to S, so that would be an edge going in the other way from the edge that's already there from S to B. If these two edges were there, then you could actually go the other way. You could reach from the target to the destination, but you're still cut off going in the other direction. Okay, so if you have a ST cut, and if you look at all the edges that belong to the cut and you remove them from the graph, then the target will be stranded from the source. So just like we posed the question of finding a maximum flow, you can analogously talk about the minimum cut. So like we said, just like we have the value of a flow, you could also talk about the value of a cut. So for instance, we had these edges here, and I think I need to bring back the capacity of this edge. So we have the edge AC with a capacity of 5, the edge AD with a capacity of 10, and the edge BD with a capacity of 5 again. So the capacity of this cut, the total capacity of this cut, is 20. And essentially we want to find a cut that has the smallest possible capacity. That would be the minimum cut problem. And you probably are already imagining that these cuts essentially are bottlenecks for flows. So if I can demonstrate to you that there is a cut which has capacity X, then you'll probably get the feeling that the maximum flow in this network from S to T is also bounded by X. So in this example, for instance, it would be challenging and indeed impossible for us to push a flow of more than 20 units from S to T. I'm not saying that 20 is achievable. That's a whole different story. A related one, but it's a different story. But all I'm saying is 20 is a ceiling. You cannot go beyond 20. Whether you can reach 20 or not depends on whether this cut is the minimum cut or whether there's one that's even smaller. So if there was a different cut, for instance, let's say the capacities of these edges were 5 and 5, then 20 is not even achievable. It's just a loose upper bound. So if you go over all the cuts in the graph, in principle, I'm not saying do it algorithmically. I'm not asking you to go and enumerate the cuts physically, but just as a thought experiment, if you were to enumerate all the cuts in the graph and list down their capacities, the cut that has, or the cuts that have the smallest capacity are your bottlenecks. You cannot push a larger flow because notice that the intuition here would be that all of this flow has to cross this cut, but the cut is capped at its capacity. It cannot handle more than 20 units of flow. Now you can formalize this using the conservation property to say that, well, if you have a feasible flow that respects all the capacities, then the value of the flow cannot exceed the value of a cut, and in particular it cannot therefore exceed the value of a minimum cut. So that's the best upper bound that you have, right? Make a list of all the cuts, make a list of the capacities, the corresponding capacities, and look at the smallest number that you have. You know that that's a valid upper bound for the amount of flow you can push. So the max flow is at most the minimum cut. And I'm not saying that I proved this formally, but I'm saying that that's an easy exercise that I would encourage you to pursue, right? But what's interesting is that once you have this upper bound, that's the tightest among all the ones that you get from the cuts, then at that point you actually have a realizable upper bound. So if you look at the minimum cut and the capacity of the minimum cut, then it turns out that you can actually be ambitious and push all of that flow. You can completely saturate all the edges in that cut, and that's possible to do. And in fact, it's possible to see why we can do this constructively by an algorithm that will be our focus next. Okay, so this is probably a good time to wrap up this conversation, where we basically set up the problem, looked at a bunch of related definitions, and just to quickly recap, we talked about what a flow is, we talked about what the value of a flow is, we also talked about feasible flows, as in those that respect capacity constraints, and we also talked about the concept of a ST cut and the capacity of a cut. We also introduced the terminology of flows saturating and avoiding edges, and that's pretty much all the words that were thrown around in this discussion. And next time what we are going to talk about is the max flow min cut theorem, which makes concrete this duality between these two notions that we have talked about so far. And we'll also take a quick look at the ford-fulkerson algorithm, which actually gives you the maximum flow. We'll talk about why that works and how that works and so on. And after that, I want to also talk about how you can decompose a flow into useful components, because that's something that will come in handy later. So that's the agenda. Next time we talk about the max flow min cut theorem as well as the ford-fulkerson algorithm. So I'll see you there.